Welcome to this video on the electrochemistry topic. We're thinking today about how we can predict reaction feasibility using electrochemistry tools that we've been learning about in previous videos. So back again to the zinc copper cell, and we found in the last video that in this cell, if we allow current to flow, there's going to be a natural movement of electrons from the negative electrode to the positive electrode. And the net result of that is that at the positive electrode, this redox equilibrium is going to shift to the right, so we're going to get reduction, and this redox equilibrium at the negative electrode is going to shift to the left, and we're going to get oxidation. And the upshot of that is that there is a cell reaction. Zinc is going to overall form zinc 2+, and copper 2+ is going to form copper. Essentially an irreversible reaction. And we call this cell reaction, this forward reaction here, a feasible reaction. And that means that without a continuous input of energy, that's the reaction that's going to happen. Now, it's important now to realize, we're going to make an important connection here, that what is happening in an electrochemical cell is only able to happen because we put a wire in between these two beakers to allow electrons to move. Without the wire, it would be impossible. Without the salt bridge to allow ions to move, it's also impossible. But we could just mix the reagents together in a single beaker. We wouldn't be able to measure a potential difference then, and it wouldn't be a very good battery. But we would still get exactly the same reaction. And here's just a picture of some zinc foil dipped into copper sulfate solution. You can see some blackness here. There's clearly a chemical reaction. The fading blue color of the copper sulfate suggesting that the copper ions are turning into copper metal. So we say that this natural reaction, the feasible reaction, happens here as well. Same reaction. Now in contrast, the reverse reaction is not feasible, unfeasible, because in that case we would need to continually supply energy in order to get that reaction to happen, because the natural flow of electrons, it's the natural flow of electrons, would tend to reduce the copper 2+ to copper and oxidize the zinc to zinc 2+. So how can we use electrochemistry machinery to actually predict whether a reaction will be feasible? There's essentially three steps here. The first step is to work out which way electrons are flowing in a given reaction. So I've just put up a reaction here between chlorine and bromide ions that forms bromine and chloride ions. I have no idea whether this reaction is actually going to happen. I can write out any redox reaction. My task is to work out whether this is actually a feasible reaction. So first thing is to work out which way the electrons are actually flowing in the reaction. And in order to do that, we use oxidation numbers. So for chlorine, it starts off at oxidation number 0, ends up at -1. So we've essentially got here that chlorine has been reduced. Bromine, therefore, must have been oxidized. We can see that from the oxidation numbers going from -1 to 0. So bromine has been oxidized. If you aren't sure about oxidation numbers, it would be good to have a look at them because they're essential for what's going to come after this. So chlorine reduced, bromine oxidized. Now the second step is to say, well, which way do the standard electrode potentials predict electrons will flow? What's that natural electron flow direction? Well, if we look at the relevant standard electrode potentials here, we find that the chlorine one is going to be the more positive, and the bromine is the more negative. We can just see from the numbers here. And what that means is that, because we saw in the last video on cell reactions that at the positive electrode we're going to get reduction, so this equilibrium is going to shift to the right. And at the negative electrode, we're going to get oxidation. equilibrium shifts left. So is that the same as what we're actually getting in the reaction? Well, it is, because chlorine is being reduced as far as this reaction is concerned, and bromide or bromine is being oxidized. The bromide ions are losing electrons. And so we would say, yes, it is, and that implies the reaction is feasible. Okay, let's see whether that is actually borne out in practice. Our prediction is yes, it's feasible. I've just shown test tubes here containing chlorine water, potassium bromide, both essentially colourless under the concentrations of our study. And then when we add these two colourless solutions, we get a sort of faint yellow colour here. We just compare it to a diluted solution of chlorine water. There is clearly a colour change here. So our prediction has proven correct. We've got bromine causing the yellow colour in this test tube. Let's try this reaction. It's a very similar reaction. We've got potassium bromide, but this time reacting with iodine. So again forming bromine and iodide ions this time. So a very similar halogen displacement reaction, but this time what we're trying to do is displace bromine from a compound by the use of iodine. So which way are electrons flowing in the reaction? Well, it's very, very similar to the previous time. Iodine is going from oxidation number 0 to -1, so iodine is being reduced. And as before, bromine from -1 to 0, so Br is being oxidized. So second bit now is to say, is that actually the natural way of electrons will flow in this reaction according to the standard electrode potentials? So let's look at the relevant potentials now. But in this case, we've got a reversal. The standard electrode potential for the bromine redox system is more positive. So this will now become the positive electrode, and the iodine will be the negative electrode. So a contrast. We go back here, the bromine was the negative electrode. Here, it's the positive electrode. So that means actually bromine will tend to be reduced, and iodine will tend to be oxidized. So, is that the same as what we are expecting according to this equation? Well, no. If this reaction is going to happen, iodine has to be reduced. But we've found from the standard electrode potentials that you're more likely for iodide to become oxidized to form more iodine than for iodine to react to form iodide. So another way of thinking about this is that imagine some electrons are released by the bromide ions, and a little bit of bromine is formed. That's always going to be happening because this is a reversible reaction. However, in this case, the bromine is much more likely to capture those electrons and reform the bromide than the iodine is to capture the electrons and become iodide. So the net effect of this is that no reaction will happen. So we're going to say this is not feasible. Let's see if that works out in practice. So we predicted not feasible. We've just got some iodine solution here with potassium bromide, and then I tipped the potassium bromide into the iodine, and I got this paler solution. Now, could that be the formation of orange bromine instead of brown iodine? Well, perhaps. To confirm it, what I've done is just added the equivalent volume of water to the iodine, and we see that these two colours are exactly the same. So there's no bromine present, it's only iodine, and therefore this reaction has not taken place. And so our prediction again has proved correct. Okay, so just to summarize, feasible reactions are those that happen without continuous energy input. They're essentially the sort of natural flow of electrons. Feasible reaction. And the direction of electron flow in the reaction must match the tendency of the species to lose or gain electrons identified by standard electrode potentials. In other words, reduction in the reaction must be species with the more positive standard electrode potential value, and the reverse is true. Oxidation must be the species with the more negative electrode potential value.